Since July, astronomers around the world have been tracking 3I Atlas as it tore through our solar system at incredible speed. But in October, just as this now notorious interstellar visitor finally became close enough and bright enough for detailed study, our view was suddenly cut off by something far nearer and overwhelmingly brighter. The Sun. Ground-based observatories that had followed its every motion for months were rendered useless at the most critical moment. We had only just begun uncovering its bizarre molecular signatures, watched it shift color not once, but twice, and even detected a strange, highly unusual tail pointing toward the Sun, a feature so abnormal that some researchers cautiously floated the possibility of artificial propulsion. At the same time, bombarded by the Sun's brutal radiation and racing along at an astonishing 68 kilometers per second, it was unclear whether 3I Atlas would even survive its close encounter with our star. Would it endure the passage or be torn apart entirely? But the story didn't end there. Beyond Earth, a network of spacecraft, space-based telescopes, and even rovers on Mars continued to watch closely as 3I Atlas plunged toward perihelion. Would it emerge intact on the other side, vaporize under the Sun's searing heat, or behave in a way no one was prepared for? In this video, we'll break down the remarkable new data gathered during 3I Atlas's flyby of Mars, reveal what unfolded while it was hidden behind the Sun, and examine the smoking gun radio signals detected by a South African telescope, evidence that could finally determine whether we're observing a volatile interstellar comet or something deliberately navigating the darkness between stars. Even before 3I Atlas vanished behind the Sun, it had already signaled that it was anything but ordinary. In late August and September, NASA turned the Swift observatory toward the object. As it continued its inward plunge, although Swift was built to detect gamma-ray bursts, its ultraviolet instruments can reveal phenomena invisible to the human eye, including the faint glow of hydroxyl, or O, radicals. These molecules are fragments of water, split apart by intense sunlight. And what Swift observed was extraordinary. At a distance of 2.9 astronomical units, nearly 3 times Earth's distance from the Sun, 3I Atlas was releasing water at a staggering rate of 40 kilograms per second. To put that into perspective, that's equivalent to a high-powered fire hose running continuously for an object this far from the Sun, where temperatures remain brutally cold. Such activity was completely unexpected. Standard comet models suggest water ice shouldn't sublimate this aggressively until much closer to the Sun. This extreme fire hose behavior suggested that 3EZZ wasn't simply releasing vapor from its surface. Instead, it was likely ejecting icy grains into its surrounding coma, grains that then melted independently, massively increasing the total surface area and amplifying the outgassing effect. But just as scientists were closing in on answers, the comet slipped behind the Sun and vanished from Earth's view. Observing 3I Atlas from space, throughout October 2025, Earth-based observatories were forced to pause their observations, as 3I Atlas passed directly behind the Sun. For astronomers, this was a nightmare scenario. The most dramatic phase of the object's journey, when solar heating would make it brightest and most violently active, was unfolding completely out of sight. Yet while Earth was blind, the solar system itself was watching. Scattered throughout space are numerous probes and observatories, some positioned perfectly to witness the event from afar. As 3I Atlas made its closest approach to the Sun, these spacecraft captured critical data that Earth simply could not. A new study, led by Qicheng Zhang of the Lowell Observatory in Arizona and Carl Battams of the U.S. Naval Research Laboratory, combined observations from 3 key spacecraft, Stereo, SOHO, and the recently launched GOES 19 satellite. These 3 spacecraft rely on coronagraphs to block the Sun's blinding disk, creating an artificial eclipse in space. Under normal circumstances, they scan the skies for violent solar eruptions. But in October, their target wasn't the Sun at all. They were tracking a comet, and what they witnessed was nothing short of a transformation. For months, as 3I Atlas pushed deeper into the inner solar system, its brightness had been rising steadily. Astronomers quantify this increase using a power law tied to an object's distance from the Sun, denoted as R. Before October, 3I Atlas was brightening at a rate of roughly R to the power of minus 3.8. That's well within expectations for an active comet, suggesting steady sublimation as material boiled off its nucleus. 3I Atlas changed color again, but once it crossed inside 2 astronomical units, the curve didn't just steepen, it nearly went vertical. The new measurements revealed a brightness scaling of R to the minus 7.5. That's an extraordinary jump. The comet was losing mass at a pace that shattered standard models of a simple, dirty snowball. It became so luminous that when it finally emerged from behind the sun, even amateur astronomers were able to capture it from Earth. These are some of the images taken of 3I Atlas during that period. A bright, expanding coma is clearly visible trailing behind the object, while the nucleus itself remains more elusive and difficult to resolve. The images were captured by astrophotographer Paul Craggs using a Dwarf 3 smart telescope developed by Dwarf Lab. The instrument proved especially capable for this type of deep sky imaging. Its live stacking feature builds sharp, detailed images within minutes, which is particularly impressive given how compact the system is. Setup was straightforward. Once mounted, it automatically aligned itself, using background stars, making it easy to lock onto comets and faint targets. Portability was another advantage. On cold winter nights, hauling heavy equipment can be a deterrent, but this setup was light and manageable enough to use comfortably without sacrificing image quality. Although the prime window for imaging 3I Atlas has now passed, a smart telescope like this can still be a powerful tool for capturing other breathtaking moments tied to the birth and evolution of solar systems, from glowing nebulae to dense star clusters, and even future comets passing through our skies. Yet the most revealing clue from this sudden brightening was not its intensity, but its color. For months, observers described 3I Atlas as distinctly red, a hue typical of dusty, organic, rich surfaces, similar to what was seen on Oumuamua. Later, observers on Earth reported that it shifted toward green, but the solar observatories saw something else entirely. Through the filters of the LASCO and SICO 1 coronagraphs, researchers reported that 3I Atlas appeared noticeably blue when compared to the Sun. A blue tint in a comet's coma is a telltale signature of gas emissions, specifically fluorescence from carbon monoxide, CO, and amide radicals, NH2. This suggests that as 3I Atlas plunged toward perihelion, it shed its dusty, dish outer shell. The sun's intense heat penetrated that protective layer, triggering the release of volatile ices buried deep within. What remained was the true heart of the object, a blue, violently outgassing core, revealed only when it ventured close enough to our star. Observing 3I Atlas from Mars, but the solar probes weren't the only witnesses. Just before its solar encounter, 3I Atlas made a close pass by our neighboring red planet, swinging within just 0.9 astronomical units, roughly 28 million kilometers from Mars. This timing was an extraordinary stroke of luck. It gave the robotic explorers already operating on and around Mars a rare opportunity to observe an interstellar visitor up close. NASA's Mars Reconnaissance Orbiter quickly turned its HIRIS camera toward the target. HIRIS is powerful enough to resolve objects the size of a coffee table from an orbit 200 to 400 kilometers above Mars's surface. If any instrument stood a chance of capturing a detailed image of 3I Atlas's nucleus, it was this one. But a US government shutdown disrupted large portions of NASA's operations, delaying the release of the images for weeks. That prolonged silence ignited speculation online, rumors that NASA had seen something unusual, perhaps even extraterrestrial in nature, and was deliberately keeping it from public view. When the images were finally released nearly 6 weeks later, the reality was far less dramatic. They revealed a fuzzy, unresolved blur, even at this relatively close range. The nucleus itself remained concealed within a dense cocoon of gas and dust, stretching roughly 1,500 kilometers across. We didn't get a sharp, pristine portrait of our interstellar visitor, but this lack of detail was still scientifically valuable. The non-detection helps researchers constrain the true size of 3I Atlas, and earlier observations from the Hubble Space Telescope already suggest it's likely no more than 2.8 kilometers wide. And the Mars Reconnaissance Orbiter wasn't the only observer at work. The European Space Agency was also tracking 3I Atlas, using both Mars Express and the ExoMars Trace Gas Orbiter. Meanwhile, NASA's MAVEN spacecraft turned its ultraviolet spectrograph toward the comet, mapping its vast hydrogen envelope, a colossal cloud of gas extending far beyond the visible coma. Perhaps most remarkably of all, the Perseverance rover, stationed in Jezero crater and fresh from uncovering what may be signs of ancient life on Mars, tilted its mast cam-Z toward the sky. In the resulting long-exposure images, 3I Atlas appears as a faint, ghost-like smudge, drifting quietly among the stars. These images may not look spectacular at first glance, but their significance is historic. For the very first time, an interstellar object had been imaged from the surface of another world. And then came the moment everyone had been waiting for. Perihelion. Is it alien tech? As 3I Atlas re-emerged from behind the sun in November, unease rippled rough the astronomical community. Harvard astrophysicist and outspoken 3I Atlas commentator Professor Avi Loeb proposed a startling idea, that the comet had fragmented, that it had exploded into as many as 16 pieces. For a moment, it seemed possible that our opportunity to study this rare interstellar visitor had been lost forever. Loeb's hypothesis was driven by calculations suggesting the comet's extreme mass loss was unsustainable. With brightness increasing so dramatically, some models implied the nucleus would have needed to break apart to create enough surface area for such intense sublimation. However, follow-up observations from the Lowell Observatory and the Virtual Telescope project quickly eased these fears. Astronomer Zhang reported that the comet appeared perfectly normal and healthy. There was no trail of fragments, no chaotic debris cloud, no signs of catastrophic breakup. The nucleus survived. What appeared to be an explosion was instead an intense but natural surge in activity, a spectacular outburst caused by the shedding of its outer crust. So yes, the comet remained intact, but anyone who has followed the 3I Atlas saga over the past several months won't be surprised that Avi Loeb raised the alarm in the first place. In a series of articles published on Medium, Loeb has argued that the comet's behavior displays what he calls anomalies, consistent with extraterrestrial technology. He focuses on two main features, a mysterious sunward jet say, N in images, and what he describes as non-gravitational acceleration, motion that keeps the object on an unusually straight trajectory. According to Loeb, the amount of mass loss required for natural outgassing to produce such acceleration would be enormous, potentially enough to tear the object apart. If the surrounding gas cloud isn't large enough to explain the observed thrust, he argues, then artificial propulsion must be considered. It's an exciting idea, one that's easy to imagine and even tempting to hope is true. But in this case, conventional cometary physics provides strong, well-supported explanations. Take the so-called sunward jet. Normally, a comet's tail streams away from the sun, pushed back by solar radiation and the solar wind. But 3I Atlas appears to display a second feature, a structure pointing toward the sun instead of away from it. Images from the 2-meter twin telescope at the Teide Observatory in Spain's Canary Islands, captured on August 2nd and released in October, show this feature in striking detail. The composite image, made from 159 exposures, each lasting 50 seconds, reveals 3I Atlas as a dark central dot, surrounded by a glowing halo. A distinct break in that luminous ring marks a jet of material, streaming directly toward the sun. Now, while it might appear at first glance as though a thruster is firing against the comet's motion, this sunward jet is actually a reasonably common phenomenon in comets. As a comet approaches the sun, its sun-facing surface heats more quickly than the shaded side. If a weak point exists in the crust, sublimating gases can erupt toward the sun. The solar wind then pushes this material back, forming a fan or spiral structure that, from Earth's perspective, can resemble a forward-pointing spike. This is not unusual at all. Similar sunward features have been documented on Comet Halley, Neowise, and Comet 67P. Next, let's consider the so-called non-gravitational acceleration. This effect, the rocket effect, is driven by outgassing and is standard for active comets. A new dynamical study by Goldie Ahuja and Shashikiran Ganesh modeled 3I Atlas's trajectory over the last century. Their analysis shows that the observed acceleration aligns entirely with the massive water and CO2 loss we have measured. The comet is indeed losing mass rapidly, just as Loeb's calculations suggested, but the nucleus's survival indicates it is dense and structurally robust, not that it is an artificial object. Furthermore, the straight-line path that Loeb highlights is largely a matter of perspective and reference frame. Objects on hyperbolic trajectories move fast enough that the sun's gravity bends their paths less than a bound orbit would, making them appear unusually straight, though they still follow predictable Keplerian and Newtonian dynamics. While Loeb's ideas serve a useful purpose by challenging assumptions, the current evidence, including the chemical identification of cyanides, water, and enormous CO2 content, BR strongly supports a natural origin for 3I Atlas. And now, the Meerkat radio telescope array in South Africa has essentially settled the debate. Meerkat detected a faint but distinct signal at 1665 and 1667 MHz, BR an absorption line of the hydroxyl radical. We had previously observed hydroxyl with Swift, but this new radio detection is decisive. Radio waves can penetrate the thickest dust clouds, giving a clear view of gas density. The detection confirms the presence of abundant water. This marks the first time radio emissions have been measured from an interstellar object. It proves that 3I Atlas is chemically similar to comets in our solar system. It is a wet, icy body venting water vapor as it heats. If it were a dry, rocky spaceship or a defunct probe, no such signal would exist. This effectively closes the case. 3I Atlas is composed of water and carbon, the fundamental building blocks of nature, not some exotic extraterrestrial material. BR so much for the alien spacecraft hypothesis. Yet, calling it a comet doesn't mean it has ceased surprising us. 3I Atlas is cooked BR. One of the major assumptions about interstellar objects like 3I Atlas BR is that they are pristine, perfectly preserved time capsules, unchanged since their parent star systems formed. But a new paper by Romain Maggiolo of the Royal Belgian Institute for Space Astronomy BR and his colleagues challenges this assumption entirely. They suggest we've been misinterpreting interstellar objets. CTs all along. 3I Atlas, according to their research, is not pristine. It is cooked. Evidence comes from chemical measurements made by the James Webb Space Telescope and the SPHERICS mission, which revealed an extreme overabundance of carbon dioxide. In typical solar system comets, water is the main driver of activity, with carbon dioxide present only in small amounts. The normal ratio of carbon dioxide to water is around 0.12. In 3I Atlas, that ratio is 7.6. Think about that. This comet contains nearly 60 times more carbon dioxide relative to water than expected. It behaves almost like a dry ice bomb. Where did all this excess carbon dioxide come from? Maggiolo proposes a fascinating mechanism. Galactic cosmic rays, GCRs, for the billions of years that 3I Atlas drifted through interstellar space, it was continuously bombarded by high-energy particles from supernovae and active galactic nuclei. These cosmic rays slam into the comet's surface, penetrating meters into its icy body. When they collide with the ice, they break chemical bonds. Models suggest that over billions of years, this relentless radiation converts simple carbon monoxide and water ice into carbon dioxide and complex organic solids. The process effectively forms a process crust, a layer of radiation-altered chemical residue extending roughly 15 to 20 meters deep. Because 3I Atlas is relatively small and eroding rapidly, what we observe today is not its deep primordial core. Instead, we are witnessing this cooked crust subtly mating away. In essence, 3I Atlas has endured the mother of all cosmic tans, and now its outer layer is peeling off. This finding implies that any object that has spent eons drifting through interstellar space will likely exhibit similar characteristics. We may never encounter a truly pristine interstellar object unless it is extraordinarily young or until one breaks apart, exposing its unaltered interior. 3I Atlas contains more CO2 than typical comets, but that's far from the whole story. Josep Trigo Rodriguez and his team compared the light spectrum of 3I Atlas with meteorites recovered on Earth. The results were astonishing. 3I Atlas's spectrum closely resembles that of Cr carbonaceous chondrites, rare primitive meteorites containing minute grains of iron and nickel metal. This suggests that 3I Atlas may carry similar metallic components. Indeed, data from the UV spectrograph on the Very Large Telescope, VLT, in Chile, detected nickel and iron in its coma as early as September. Analysis revealed an unusually high nickel-to-iron ratio. Unlike any comet previously observed in our solar system, even 2I, Borisov, the interstellar visitor of 2019. Interestingly, the VLT team noted that the nickel-to-iron ratio declined as 3I Atlas approached the Sun, hinting that Comet 3I could soon become indistinguishable from solar system comets in this regard. Why does the presence of metals matter? When water ice melts within the comet's porous crust, heated either by the Sun or our internal pressure, it can come into contact with these metallic grains. In the presence of metal catalysts, water and carbon compounds can undergo Fischer-Tropsch reactions. These are exothermic processes, releasing heat as chemical bonds are restructured. This sets up a self-reinforcing cycle. The heat melts more ice, which reacts with additional metal, releasing yet more energy. Over time, this process builds pockets of extreme pressure beneath the crust until the surface ruptures, sending a jet of gas and dust blasting outward. This type of activity, essentially cryovolcanism, could account for the sudden surge in brightness, the formation of jets, and the massive ejection of material. It also explains why the coma is enriched with nickel and iron gases.
What's next for 3I Atlas?
So, what lies ahead for 3I Atlas? As of November 2025, the comet has emerged from the glare of the Sun. It survived perihelion, though the intense mass loss has likely reshaped its surface permanently. Now it is outbound, hurtling away from the Sun and back into the interstellar void. But there is still more to learn from this remarkable object. At the time of this release, 3I Atlas will have just passed its closest approach to Earth. Looking ahead, on March 16, 2026, the comet will fly approximately 0.35 astronomical units from Jupiter, making one of the closest passes relative to a gas giant ever recorded. Models indicate that this approach will take it inside Jupiter's Hill sphere, the region where the planet's gravity dominates over the Sun's. While 3I Atlas will not be captured, it is moving far too fast. Jupiter's gravity will give it one final gravitational nudge before it departs the solar system entirely. Importantly, this flyby presents a potential observation window for the Juno spacecraft, currently orbiting Jupiter. If Juno remains operational, it could provide a final close-up perspective of this interstellar traveler from the outer solar system. The saga of 3I Atlas is far from complete, yet in just a few months, it has already taught us more about interstellar objects than decades of theoretical work ever did. It has revealed that the space between stars is far from empty. It is a cosmic radiation furnace, physically altering the bodies that drift through it. It has shown that even small, seemingly insignificant objects can harbor complex chemical engines, capable of powering jets and surviving the sun's searing heat. And while it may not be an alien spacecraft, a small rock that has traveled billions of years, bearing the marks of its journey across the galaxy, is, in its own way, just as extraordinary.